Right. Before the break, we were talking about the calculation of value at risk assuming the Black-Scholes model. We discussed the scenario where we had a single asset, and we also discussed the scenario where we had two assets comprising the portfolio. This expression or this formula can very well be extended to a number of assets, say n assets, and for n assets we have this expression, which is again a very standard expression. Sigma p square for the portfolio, that is the variance of the portfolio, is given by double summation p I p j rho I j sigma I sigma j, and this expression follows from the earlier expression. Delta p per day can be written as the sum of delta p of the constituent assets of the portfolio, which can be written in this form, delta p upon p, and which, because we are assuming mu to be 0 in each case, which can be simplified in this form. And this Z I expression, again this has a mean of 0 for each I, whatever see this Z will be different for each constituent of the portfolio, for each asset that goes into the portfolio, and therefore, because the Z is different for each asset that constitutes the portfolio, we have this term coming up, rho I j, which emanates from or which originates from the correlation between different CIs. See, suppose there are two assets forming the portfolio, there will be two standard normal variates, one associated with asset A, the other associated with asset B, and when you take the variance of the expression, the covariance term or the covariance between these two standard normal variates will also come into play, will also make a representation in the covariance, and that will be this particular term. Right. So, now we come to so far we have talked about cash assets, in the sense the assets that are directly affected by market prices. For example, there could be stocks, there could be commodities, there could be commodities, there could be stocks, there could be currencies, and so on. Let us now move to bond portfolios. For bond portfolios, there are three standard approaches for working out the value at risk. We have the duration based approach, we have the cash flow mapping, and then we have the principal component analysis. We will take up one by one. Let us first start with the duration based approach. In the duration based approach, you would recall, in fact, let us start with a single bond. The present value or the price or the intrinsic value of a bond is given by the present value of all future cash flows discounted at the appropriate rate, which, if the left hand side is to represent the market price, the discount rate will be the YTM, right. So, if that YTM is expressed as a continuous compounded rate, we get this expression Pi is equal to this expression, where the coupons are paid at intervals t equal to 1, t equal to 2, t equal to 3, and the final coupon at t equal to capital T, which represents the maturity. Please note, this cash flows, the final coupon or the final cash payment, that is at t equal to capital T, would also include the principal. In fact, if the principal is distributed in redemption, the principal is redeemed in more than one installment, that can also be captured by this model. You simply have to change the value of C t. Instead of using it, basically it represents the total cash flow, whatever the source of the cash flow may be, whether it is coupon, whether it is a principal, or whether it is both, right. So, whatever that case may be, P t is equal to the present value of these cash flow payments emanating from the bond, and differentiating that with respect to y, we get this expression, which gives us, on dividing by p and taking dy to the right hand side, we get this expression into dy. Divide both sides by p and take this dy to the right hand side. Okay. Now, this expression t c t e to the power minus t y divided by p t is given a name, it is called the duration. We have talked about it in an earlier lecture. It is a similar expression, except for the fact that here I am using continuous compounding, there I think I used annual compounding, that was the only difference. The philosophy, the concept is absolutely identical. parallel congruent, but only thing is because of continuous compounding, the discounting factor is slightly different. So, this is my duration, dy comes here, therefore, the percentage change in price is given by minus duration into dy. Now, we come to a portfolio consisting of a number of bonds. For a portfolio consisting of number of bonds, the change in price of the portfolio will be the aggregate, the algebraic sum of the change in prices of the constituent bonds, which is captured by this expression. You write it at this expression, and this expression delta p I upon p I is nothing but d I into p I, as you can see here, d I into d y. So, this and this are this particular factor, and this p I appears as it is. Now, that means what? We multiply and divide by p, we multiply by this p and divide by this p, that does not change the scenario. P is the total value of the portfolio. So, multiplying and dividing by p, I write the expression within summation as d I into p I upon p, and if you look at this p I upon p, it is nothing but the weightage of asset I or bond I in money value over the in the total money value of the portfolio. Weightage of bond I in money value over the total money value of the bond, that is the weightage of the bond. So, this expression within summation is nothing but d I into w I, and which is nothing but d p, where d p is the duration of the portfolio. So, the right hand side becomes this summation terms becomes d p. So, we have minus p d p into delta y, and therefore, if I take the standard deviation of delta p, this being non-stochastic, d p is non-stochastic, p is the price at a given point in time. So, it is non-stochastic, it is price at t equal to 0. So, it is non-stochastic. The only stochastic term is delta y. So, we have sigma p is equal to d p into sigma of the delta y, sigma of the yield rates. Before I move to an example, there is a very important assumption here. I must emphasize that assumption. You see, my portfolio will consist of a number of bonds. These bonds will more likely than not have different maturities, and therefore, be influenced by different spot rates or spot rates of different maturities. Now, it is not necessary that the term structure of interest rates be horizontal all the time. That means, the interest rates need not be the same for all maturities, or let us put it another way, the interest rates may not change by the same amount at a given point in time. Say at t equal to 0, I am investigating the change in interest rates. So, there is a change in interest rates. It is not necessary, there is a macroeconomic phenomenon, and as a result of it the interest rates change. It is not necessary that interest rates for all maturities change by the same quantum, same value, same absolute value. The 1 year interest rate changes by 0.5%, the 2 year interest rate changes by 0.5%, the 10 year interest rate changes by 0.5%. It is not at all necessary. It obviously depends on demand and supply for money corresponding to those maturities. Therefore, now in that context, in the context of what I have just mentioned, look at what I have done here. What I have done here is I have taken delta y outside the summation. Because I have taken delta y outside the summation, I am implicitly assuming that the delta y is the same for all maturities. In other words, I am assuming a parallel shift in the interest rates, and this in fact happens to be the biggest drawback of this model. This model assumes that the shift in interest rates as and when it occurs is a parallel shift, and therefore, bonds of all maturities or interest rates corresponding to all maturities shift by the same absolute amount when the shift takes place. In other words, delta y is independent of maturity. Whenever the delta y shifts, it shifts by the same amount. So, that is very important, and that forms the fundamental flaw or the fundamental shortcoming, fundamental limitation of this model. That is what restricts its application, that we assume that the shifts in interest rates or shift in yields shift in yield curve is parallel. The term structure of interest rate shifts parallelly whenever, as and when it does shift. This delta y we assume has nothing to do with maturity, nothing to do with the various bonds which are here. See, what I have done is I have taken delta y independent of I, that means whatever bonds, those I bonds A, B, C, D I have in my portfolio are not are affected similarly by this delta y. If they are of different maturities, does not matter, they are still affected similarly. The delta y for each of them is the same. That is the important constraint of this model. So, maturities, the shift of interest rates is the same for all maturities, that is a flaw. Right. So, this is an example. A company has a position in bonds worth $6 million. The duration of the bond portfolio is 5.2 years. Assume that only parallel shifts in the yield curve can take place and the standard deviation of daily yield is 0.09%. Use the duration model to estimate the 20-day 90% value at risk. The z value is given to us, z value for 90% is 1.28. So, portfolio value is 6 million, portfolio duration is 5.2 years, sigma y is 0.09%, that is 0.0009, sigma w is equal to d into p into sigma y. So, that comes to 28080 and 20-day 90% value at risk comes to be 160739, a pretty straightforward problem. Now, we come to a very interesting approach which is called cash flow mapping. Now, what we do here is, you see, again I come back to my bond portfolio. My bond portfolio will consist of different bonds, or even if it consists of a single bond. That bond may have a maturity which is not a standard maturity. See, bonds of certain maturities or data in respect of bonds of certain maturities are available or are monitored and are published or presented over electronic media on a regular basis. What are those standard maturities? Let us first note that the standard maturities are 1 month, 3 months, 6 months, 1 year, 2 years, 3, 5 years, 7 years, 10 years and 30 years. These are standard maturities and data on volatilities of these bonds, price volatilities or return volatilities of these bonds is available on various financial information databases regularly updated for information of the investors. Now, the point is, my particular bond or a portfolio of bonds may not fall in line with these maturities. For example, which we are going to consider just now, we may have a bond of a maturity of 0.3 years, or we may have a bond of a maturity of 1.2 years, or we may have a bond of maturity of 1.8 years. Now, the data in respect of these types of bonds will obviously not be available, and therefore, it would be very difficult for us to work out the value at risk of our portfolio. One approach which is very useful and which is very intuitive is to bifurcate our particular bond, any cash flow of relating to our bond, be it a coupon payment or be it a maturity payment or whatever, any cash flow relating to a particular bond into two parts. Those two parts would relate to the immediately preceding standard maturity bond and the immediately succeeding standard maturity bond. For example, if I have a 0.3 year bond, 0.3 year bond means about 3 months and something. So, that would be mapped into a 3-month bond and a 6-month bond. And similarly, if I have a 1 year 1 month bond or a bond maturing after 1 year 1 month, I would map it to a bond having a maturity of 1 year and a bond having a maturity of 2 years. And if similarly, if I have a bond of a maturity of 8 years, I would map it to a bond of 7 years and a bond of 10 years. So, and in fact, this would also be, this could all, you see, now there is another important issue here. Suppose I have a bond, suppose I have a bond, let us say I have a bond of a maturity of 1 year 1 month and it pays interest semi annually. Say 1 year 1 month, that means I will have a payment at the end of 1 month from now, then I will have a payment at the end of 7 months from now, and then I will have a payment at the end of 1 year and 1 month from now. This will be the final payment. Now, what I have to do is this bond, because it is a 1 month bond and there is 1 month bond is a standard bond, no mapping is required in respect of this cash flow. As far as the 7th month bond is concerned, this is to be paid at the end of 7 months, the coupon payment, please note. This is a coupon payment, this is a coupon payment, this is a coupon payment plus redemption. A is a coupon payment, B is a coupon payment, C is a coupon payment plus redemption, total let us say 1 year 1 month, right, 1 year 1 month, right. Okay. So, this 1 year bond, this 1 month bond would be straight away mapped to the 1 month standard bond, there is no problem. About the 7 month payment, this would be mapped to the 6 month standard bond, 6 month standard bond and the 12th month standard bond, that is 1 year standard bond. How the mapping is done we will come back to immediately, and this next payment of principal and the final coupon would be mapped to this 12 month bond or 1 year bond and the 2 year bond. So, this is how the scheme operates. All my cash flows emanating from the bond portfolio, this set of bonds, entire set of bonds, they are aggregated in terms of their respective time points in time at which they are made, and then each such cash flow is bifurcated, is split into the immediately preceding standard bond and the immediately succeeding standard. Now, how it is done? I will explain with an example. A 3-year 0 coupon bond with a principal value of $50,000, this is the face value, this is the redemption value, and the redemption value is at 0.3 years from today, that is slightly more than 3 months, is mapped into positions in a 3 month bond and a 6 month bond. The 0.25 year and the 0.5 year spot rate, this is the 3 month rate, this is the 6 month rate, are 5.50% and 6% respectively. These are the two spot rates of the 3 month maturity and 6 month maturity. These are the rates applicable to 3 month bonds and 6 month 0 coupon bonds. Daily volatilities of the 3 month and 6 month 0 coupon bonds are 0.06% and 0.1% with a correlation of 0.9. We are to do the cash flow mapping. Now, because it is a 0.3 year cash flow, we have one cash flow and that is only one cash flow is going to take place, and that cash flow is going to be of $50,000 and that cash flow is going to take place at 0.3 years. Therefore, it is going to be mapped into the 3 month bond and the 6 month bond. Now, the spot rates are for the 3 month and 6 month bonds are given to this and given as 5.5% and 6% respectively. This enables us by linear interpolation to work out the spot rate corresponding to 0.3 years. This enables us to work out the spot rate corresponding to 0.3 years, which is the maturity of the bond that we have to do map. Let us call this bond X, let us call this bond A, and let us call this bond B. So, we have to map X into A and B, and the spot rate corresponding to X is worked out by the interpolation of the spot rates for A and B at 5.60%. The present, you see, now the payment of 50,000 is to be made at t equal to 0.3 years. That what is the present value? That is the amount that will have to be mapped, and the present value works out to 50,000 divided by 1.056 to the power 0.30, that is 49189.32. This is the amount which will have to be mapped into X and Y, sorry, to A and B. Now, we want that the volatility of X should match the volatility of the bifurcation. Please note, it is a notional bifurcation, it is not a physical bifurcation. We are not physically converting our bond to bond X to A and B. We are simply doing a notional exercise in order to be able to work out the value at risk precisely. That is it, that is the objective. No physical transfer is taking place. The volatility of the 3-month and the 6-month bond is this much. We want that the volatility of X should be equal to the volatility of the combination of A and B in the appropriate proportion after bifurcation of X, or when X is split up into A and B, the combination of A and B due to the splitting should have the same volatility as the volatility of X. The interpolated volatility of X is 0.068%. This is done by linear interpolation, just as we did for the spot rates. Now, let us assume that out of this amount 49,189, X percent or X proportion is mapped to the bond A and 1 minus X is mapped to the bond B. Then what will be the volatility of this portfolio comprising of A and B in the ratio X and 1 minus X? That is given by, we know the formula, we have just done it earlier. The volatility of A squared into X square, volatility of B squared into 1 minus X square, the composition, plus 2 into correlation into volatility of A into volatility of B into composition of X and composition of A and composition of B, or content of A or proportion of A and proportion of B. This is a standard formula again, and the left hand side we have already worked out by linear interpolation. So, if you simplify this quadratic equation, we find that X is equal to 0.70. In other words, about 76% of my 49,189 goes to my 3-month bond, and about 24% or slightly under 24% goes to the 6-month bond. That is precisely what is here. 37,397 goes to A and 11,793 goes to B. So, this is how the splitting or the cash flow mapping takes place. Then we have the third approach, which is called the principal component analysis. Principal component analysis is largely, or may I say entirely, a software oriented approach. The standard statistical software like SPSS and others probably have this particular package with them. I think Excel also has an add-on on principal component analysis, although I have not done it. But the philosophy of this particular analysis is that we identify the factors which relate to or which influence our bond portfolio. Obviously, there will be various interest rates of various maturities. Interest rates with various maturities are what are going to influence our bond portfolios. What we try to do is, because there could be a huge spectrum of interest rates which would influence our portfolio, we try to reduce the dimensions of the problem. In fact, principal component analysis is a technique of dimensional reduction, where given a certain amount of data having a large number of dimensions, we try to extract, or the software does an extraction process whereby it brings out certain factors, or it extracts certain factors which are mutually uncorrelated. I strongly emphasize this, which are mutually uncorrelated. The factors that are thrown out by the principal component software will be mutually uncorrelated, and which will be such that these factors would be less than the number of factors that are originally given in the problem. For example, the spectrum of interest rates, they would be less than that, but they would provide a significant proportion, or they would explain a significant proportion of the variance of the data that is provided to us, and as a result of which we do not lose much information by using a lesser number of variables, lesser number of factors to represent the same problem, and in addition to that we have a massive advantage of using uncorrelated variables, uncorrelated factors, which is a huge advantage. I will not go into the theory of this particular principal component analysis. I will leave it as a part in the of the PPT for those who are interested. Let us do a quick problem on this. Suppose that the daily change in the value of a portfolio is, to a good approximation, linearly dependent. Linearly dependent is important. Principal component analysis brings out linear factors. This is very important, and they are uncorrelated as well. Linear and uncorrelated. Linearly dependent on two factors calculated from a principal component analysis. The delta of a portfolio with respect to the first factor, delta of my portfolio, given portfolio with respect to the first factor is 6 and with respect to the second factor is -4. The standard deviations of the factors are 20 and 8. What is the 5-day 90% value at risk? Let the portfolio value be represented as P is equal to alpha F1 plus alpha 1 F1 plus alpha 2 F2. F1 and F2 are the two factors that are thrown out or that are available from the principal component analysis. Now, delta 1 is with respect to the first factor. So, it is the rate of change or the partial derivative of P with respect to the first factor, and that is given at 6. This gives me alpha 1 is equal to 6, and similarly I get alpha 2 is equal to -4. Hence, we have P is equal to 6 F1 minus 4 F2, delta P is equal to 6 delta F1 minus 4 delta F2. Because F1 and F2 or delta F1 and delta F2 are uncorrelated, what do I get? Sigma P square is equal to 6 square into sigma of F1 square plus 4 square into sigma of F2 square, that is because rho 1 2 is 0. So, there will be no cross term. There will be no cross term because, as I mentioned, the two factors are uncorrelated. They are provided as such by the system. The software or the principal component analysis technique ensures that the factors F1 and F2 are uncorrelated. So, 36 into sigma 1 square plus 16, this 36 comes from 6 square, sigma 1 square is the standard deviation of first factor or variance of first factor, minus 4 square gives me 16, and sigma 2 square is the variance of second factor. Substituting the respective values, I get sigma p is equal to 124.19, and the rest is as usual. Z is equal to 1.28 for 90%, root 5 because of the 5-day, and this is the standard deviation, and we get the value at risk as 355.46. Now, we come to a portfolio comprising of derivatives. Now, in the case of a portfolio which involves a derivative, again the process is more or less absolutely parallel to what we had for the underlying asset, for the cash assets, for the stocks. So, let us see how we go. Now, delta is equal to delta p upon delta s. This delta means the delta, the option Greek delta, that is the small delta, and this delta is the change in price. So, please note the notation, there are too many deltas floating around, but small delta is the option delta and capital delta is the change in price. So, change in price of the option or change in price of the derivative upon change in price of the underlying asset. Therefore, I can write change in price of the derivative as delta, a small delta into delta capital delta of S. I can write this as this whole expression multiplying and dividing by S. Delta remains as it is, S is multiplied, S is divided, delta S remains as it is. Now, this expression, if you recall, is nothing but the Black-Scholes model. If I use the Black-Scholes model, this expression takes this form: S delta mu dt or delta t as you like plus sigma z under root delta t. Now, if delta t is equal to 1, that means we are talking about a daily change in price or a 1-day change in price, 1-day change in price of the underlying of the derivative. Then we have delta p per day, and if you are ignoring this mu term, because of its smallness, we have simply S into delta into sigma of day S into delta into sigma day into Z, and this under root dt or delta t becomes 1 because you are talking about 1 day, and sigma becomes sigma per day, S delta sigma per day into Z dt is 1, root dt is 1. So, if you compare this with what we had for the underlying asset or for the cash asset, you find that it is absolutely the same. This expression is absolutely the same, but for the additional term delta. What is this delta? This delta is the rate of change of the portfolio with respect to the rate of change of the portfolio with respect to the rate of change of the underlying asset. Rate of change of the call option, rate of change of the derivative with respect to the underlying asset. Why has this come? That is very interesting. Why this has come is obviously because this has come because what is a derivative? A derivative is a function of the underlying asset. The price of the derivative is a function of the price of the underlying asset. The value of the derivative is a function of the value of the underlying asset, and therefore, when we talk about the price change of the derivative, we have to incorporate the rate of change of value of the derivative or price of the derivative with respect to the change in the value of the underlying asset, and then put there the change in value of the underlying asset. Is something like you have in calculus, you have d of y is equal to dy by dx into dx. This term is nothing but delta. So, when you are talking about a function of x, you want to work out the change in value of the function, you have to incorporate the rate of change of the function with respect to the independent variable, and then multiply by the independent variable. So, that is precisely what is happening. This delta here is nothing but this delta here, the rate of change of the price of the derivative with respect to the underlying asset, and then you multiply by the rate of change of the underlying asset. So, that is how this comes. This is again elementary, the same thing happening here, because we have different ZIs corresponding to different portfolio values. Therefore, we have to introduce this expression rho ij, and delta I delta j represents the various constituents of the portfolio. The quadratic model is slightly more extensive, slightly more elaborate, carries a bit of nuances in the sense that we are truncating the change in price at the second order in the Taylor series in terms of the derivative of this underlying price, and therefore, we introduce gamma. Gamma is nothing but the second derivative of the price of the portfolio with respect to the underlying asset. The rest of it more or less is the same. We have this expression for delta p. In fact, this is for quadratic model where you are not truncating the price change at the first term of the Taylor series, but truncating it at the second term of the Taylor series. A slight improvement in results, of course, naturally more accuracy will be there, and of course, at the cost of more calculations, more complexity. Right. So, this is an example where we have got a portfolio of options. Microsoft at AT&T, Microsoft have a delta of 1000, AT&T have a delta of 20,000, Microsoft stock price is 120, AT&T stock price is 30, volatilities are given 2% and 1%, correlation is 0.3. So, literally everything is given. You are simply to put the respective values in the formula, and you get sigma p is equal to 7099, a pretty straightforward problem. This is SA, this is sigma A, this is SA, this is delta A, sigma B, and this is delta B, this is SB, this is sigma B, and this is the cross term, and this is what we get. Another example, suppose you for a forward contract, let us have a look at it. Some time ago a company had entered into a forward contract to buy sterling 1 million for dollars 1.5 million. That's what the forward contract was originally envisaged. The contract now has 6 months to maturity. The daily volatility of 0 coupon sterling bond when it is translated to dollars is 0.606%. Volatility of a 6 month coupon 6 months 0 coupon dollar bond is 0.05%. The correlation between the two returns is 0.8. The current exchange rate is so much. Now, the company has entered into a forward contract to buy sterling 1 million. So, it is long in the sterling bond, it is short in the dollar bond. The value of the sterling dollar value of the sterling bond will be calculated at current price, and that is 1.53, that comes to 1.492. Dollar value of the dollar bond, which was because the contract envisaged delivery of $1.5 million. So, it will be 1.463. This is the important part. This is the catch in this problem. The rest of it is straightforward. Because we are a long position in a sterling bond, we work out the sterling bonds position as of today at today's rate, which is 1.53. As far as dollars are concerned, we have to pay dollars at the rate at 1.5 million. That remains unchanged. That is what the forward contract envisages, and therefore, so this figure remains unchanged. It remains at 1.463, and then we use the standard portfolio formula for calculating the sigma of the portfolio, and they work out the value at risk. So, this is another problem. So, with this I conclude this course on financial derivatives and risk management. It's been a pleasure bringing this course to the viewers, and I thank all of you. There obviously been an occasional slip and maybe a blackout, a couple of blackouts as well, for which I do apologize. But I hope you will enjoy this course, and you have enjoyed this course for those who have seen it. And for any questions, any queries, you are always welcome. Thank you very much, all of you.